Hi, I'm good. How are you?
Yeah.
Oh, these are wow. I don't have someone.
This is the Sure, yeah. So
Okay, I can't wait. Yeah.
no. Feel free to get some of the snacks. Yeah. So this is so for the winner of this cheat sheet contest, everyone is the winner. Not because I forgot the contest, but yeah. So basically, I brought some snacks for you to have during the session. Feel free to have some of them. Thank you.
Yes.
Okay. Good. No.
Thank you.
Slightly less. I'm just trying to pass. So sorry.
Oh no. I'm sorry. What do you need? Like regular?
Obesity.
Okay.
Yeah, I mean exactly, but
No, it's that's not downplaying.
yeah,
The
but
difficulty
I
of
think the problem that women is that I've been in math class for so long, so I should have started doing how to
That's the real thing.
I don't know who was the type of job.
That was last semester. Like, oh, I just like look at it and memorize it.
Mhm.
No,
No,
it's
it's not.
application and
It's,
credit
and it's also like, you know, like index cards for me and stuff like that. It's kind of just like first five, nothing like reading.
Oh,
Just,
no.
You
No.
know, like I
Yeah, no,
feel
That's,
infinitely
it's an easy
smarter.
course. It's just a lot of
now
reading, but
as a result.
it's just like
So, yeah.
they don't make it awful for you.
I'm
If we
reading
had to
grades, I
write
don't know if
papers,
it's accurate.
Alright.
Yeah, I don't know if I would have enjoyed that at all.
So the final exam.
Yeah.
Yeah, I gave them like a really review. Like the teacher.
So did everyone get the final exam back, or is there anyone who didn't? Okay, good. So like the midterm, yeah. So for the final exam, it'll be 2:45 to 4:45 on May 8th. Location will be announced soon. And it's cumulative, as you may know, and you should bring your calculator or your phone, just like the second midterm. And then there's cheat sheet allowed, which is also hint, which should be handwritten and one-sided, just like the last time. And there's no cheat sheet contest this time because I cannot the group board, basically. I wouldn't have the opportunity to do that, so. And then, so there is a class or a lecture on mediation analysis tomorrow. So I will have a review session for that from 5 to 6:30 on May 1st at this place. This is an extra session, so you don't have to. It's not a requirement for you to come. And but it'll be recorded via YouTube as well. So if you cannot make it, that's fine. You can just keep all this. Watch the YouTube. Yeah. And then for the attendance, I think it's efficient. When I send you an email, only when you're absent more than 4 times, if that's okay. So like your attendance score is only decided determined if based on whether you were absent more than 4 times or not, right? So other than that, there won't be any impact on your grade anyway. So I think I'll send you an email only when you're absent more than 4 times. But if you would rather know your absence records, feel free to let me know. Like, feel free to send me an email. I'll just send you an email about your attendance records, even if you were absent less than or 4 times. Good. Any questions about it? About that? Nope. All right.
Can I ask a question about the final exam? So this review session on mediation analysis, that's just going to be on tomorrow's material for Wednesday. That review session is just to look at what we are doing tomorrow.
Yeah, so the extra session will be just about mediation analysis, actually.
Okay, and we don't have class on Monday, correct?
No.
Okay.
This is the last, this is the last section. Yeah. Any questions? No? Alright. Let's review the midterm 2. So the mean is 83%, 83.7%. The median is 86.7%, which means that you did very, very well, right? So you're doing really great in this course. And then obviously you should let me know if you have any questions about the grading scheme, stuff like that. But overall, I would say you're doing really well in this class. And then I'm sure you will be doing great in the final as well. Good. But before starting the review of the last 2 lectures, I want to cover some of the or review some of the questions in the midterm. Actually, so there was a question about. Oh yeah. So let's talk about the mechanical and thought questions. Number 2. Right. So you guys have the midterms with you, right? If you don't, that's fine. I'll just write them down for you. Right? CA. And then the question A was,
asking that considering Z as a candidate instrumental variable, use Rice path rules to express the instrumental variable's estimate for the causal effect of T on Y in terms of path coefficients. So in that case, you will be using covariance between Z and Y divided by covariance between Z and T, right? And that would be AB divided by A, so right. Good. And for question B, you would have covariance between P and Y, covariance between P and T, CAB, CA, and that becomes B. Right? That should be pretty okay, right? But the question C was asking if a researcher claims that a valid instrumental variable must not cause the outcome directly, but must cause the outcome indirectly. Do you agree with this? Why or why not? Right? So if you remember, there are two assumptions of IB. The first one was relevance, which means covariance between Z and T is not 0. The second one is exclusion, where covariance between Z and EY is 0, right? They're noted as that one, right? Actually, some of you interpreted B as relevance, right? But it's not exactly right. Why is that? Because if relevance is, like, if B were speaking to the relevance assumption, it should say, instead of the outcome, it should say treatment directly, or whatever.
So if it causes
Be associated. Oh, what?
if it causes the treatment directly, then isn't it still causing the outcome?
Oh, what?
If it's causing the treatment directly, then isn't it imply that it's causing the outcome sort of directly?
No, not really, because if let's think of a situation where there's no treatment effect. In that case, this is not same as B, right? We're not assuming there is a treatment effect. We're not necessarily assuming that. So this does not speak to the assumption of relevance. They are actually in combination speak to exclusion assumption, but what's wrong here is they should be really be associated with instead of cause. Because exclusion assumption really tells you that covariance between the instrument and the error term is 0. Meaning that instrument variable must not be associated with the outcome directly, but must be associated with the outcome indirectly. Does that make sense? Any questions? Nope. All right. So in combination, they both speak to the exclusion assumption if you're saying must not be associated with the outcome directly, but must be associated with the outcome indirectly. Actually, an example of this argument could be the question B. Here, P is used as an instrumental variable, right there. Right? As the question B suggests, P can be used as an instrumental variable, even though it is not causing the outcome directly, or it's not causing the outcome indirectly. Does that make sense? Any questions? All right. I think this is one of the hardest questions in the midterm. I mean, that's why I specifically covered that example in the section, but I mean, that's, yeah. Any questions? No? All right, good. And then, so there's that. And then there's another question I would like to review, which is short answers. Question 8. Oops. Educational attainment. B1, parental aspirations. B2, parental SES. B1. So question B was asking, what would the measurement error in PA affects the slope estimate of SES, which is data 2. That was the question, right? So verbally, you can say that if there is a measurement error in PA, that means that there is remaining parental aspirations going on that is latent, that is not captured by the measured parental aspiration. So even if you control for PA to get the B2 hat, right? There will be still confounding relationships going on. Does that make sense? It can be graphically demonstrated as A latent let's say PSCS is confounded by this one. Oh. Yeah. Good. Let's say this one. You could think the other way as an arrow, but if you think this way, if you think this way is right, and then you can think of PA asterisk, the latent parental aspiration, as the confounder of the relationship between PSCS and EA. There will be some measurement error right there. So, to get the coefficient of PSCS, you will control for PA. Good. And what happens? What happens is there will be still some confounders left, some confounding going on. Does that make sense? Even if you partially control for the latent PA through this one, there will be still remaining variance in here. Does that make sense? Yeah. All right. So your answer could be there will be still some confounding relationships if there is measurement error in PA, as if the direction of the bias will be the direction of confounding effect when you were not to control for PA. Good. Any questions? Nope. All right. Then let's move on to the review of the last lectures. So we talked. For the review of the last lectures, I'll focus more on the data exercise part rather than just for explanations of the model per se. So I'll quickly review the last lectures through with the slides, but the reviews will be focused on data exercises. So it'll be a fixed effects model's motivation is basically controlling out all the time constant unobserved confounders or group constant, all the variations shared within. You're controlling out all of them. Okay. And it's mathematically equivalent to adding individual dummies for beta coefficients. And for the estimation of beta coefficients of interest. And the most important assumption behind fixed effects is that it is strict exogeneity, which means that treatment should not be affected by pre-treatment outcome or post-treatment outcome as well. Right. So an example in the lecture was fatherhood premium using fixed effects. It could be still biased due to the possible violation of strict exogeneity because, so simply put, it is it's about whether you you get a raise purely because you got married, or you got married because you have higher wages. There is a two directions of arrows can be going on, right? And then you never know. You can you never know, but you cannot know whether one of these things is true by fixed effects. Oh. You're making an assumption that, oh, fatherhood, if there's a positive relationship between marriage and wage, then you're making an assumption that, oh, marriage must have played an independent role in shaping wages, not the other way around. Good. Any questions? That's strict exogeneity. Reverse causality. It's really, really reverse causality. And we covered MLE and panel models. And panel models are simply an HLM with panel data. And so the motivation there was this is firm A, firm B. This is firm A. Precisely because they do have different intercepts or different means. They have positive errors on average right there for firm B, and they have negative errors for firm A on average because the intercepts are different. And therefore, there's correlation among errors. I would like to make a technical note that I didn't make in the lecture because I didn't want to confuse you or anything. But so they are numbers, right? Errors are technically numbers, right? So they cannot have correlation among them. But what I try to make a point here is that if you sample multiple times, then the data points will look like that. And the data points will look like that, data points will look like that, and data points will look like that. And these points will have a relationship with each other, correlation with each other. Good. That's what I meant, technically. But still, we just sample one time in real research. Good. Any questions? Nope. All right. And then to deal with this situation, we come up with an HLM and or random intercepts models to be more specific in our lecture. right? We didn't assume, we didn't think of a situation where slopes are different across groups, right? We assumed intercepts differences only. Right? And regardless of, so depending on whether you control away all the intercept differences or not, you can divide intercept models into fixed effects model and random effects models. Right? So fixed effects models are robust to indigeneity from panel level characteristics, but inefficient compared to random effects models. As you can see from the slides right there. And random effects models are subject to indigeneity from panel level characteristics, but efficient compared to fixed effects models. That's the key takeaway of the last lecture. Any questions? Am I going too fast or? Nope. All right, then let's talk about, let's cover Stata exercise. So in week 13, then there will be a panel models folder. So you can download them. And there will be another folder called LGCM, which is optional. This is latent growth curve modeling, which we did not cover in the lecture. And there is a Stata exercise for that, but this is also optional as well. If you're interested, you can ask me questions about it, but this is completely optional. For panel practice, we will focus on the panel practice Stata exercise for today. Good. All right. Make sure to change the directory right there. And let's work with the data. So, so the data set here is, I basically took the data. I made up the data on adults' depression level. And the age here is 25 to 64. So we're looking at the relationship between the depression level, which is the outcome of interest, and gender. Not gender. Yeah, gender actually. Or other variables. I will, yeah. And other covariates include number of close friends and satisfaction with family life. And if you look at it, look at the data window, then the ID here, 14201, means this is person ID. As you can see, there are 3 waves. 1, 2, 3. So this person is followed by 3 times. Does it make sense so far? Good. Yeah. And then the depression level is depression scales. Level is 2.625, 2.375, and 2.5. And the gender is male, 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 which is time constant. And close friends is right there, and family satisfaction looks like that. And I'm not sure I include the variable here in the model, but whether you got bullied in the childhood or not was included, I think. But I think I did not include that in the model eventually, so I need to change that variable. But, so don't worry about that here. Leave here. So the alcohol interest is depressed, and the independent variables are female close friends, close friend, and family satisfaction. Okay. And this is called a panel data set because these are called panel data because it is a combination of cross-sectional data and time series data. Cross-sectional data means that you have multiple units of analysis in the data. You don't have one person in the data, right? And time series data means that there is multiple time points where a certain unit of analysis is followed or measured repeatedly. So that's why panel data are called cross-sectional and cross-sectional time series data. They are synonyms. It's a special case of nested data because time points are nested within each panel, but the time component makes the panel data really unique actually because of in terms of causality. But we're not going to focus on that in this class. But it's basically about past something that's going on in the future cannot affect your past here, and that's what makes panel data really interesting and difficult to analyze. But yeah. There will be clustered errors because of the data structures, and then appropriate modeling is needed. Right. Yep. And that's why we're learning all these panel models. That's opening the section here. And you can divide panel data into certain types. The first one is balanced versus unbalanced, meaning that everybody has the same starting point and end point, or the number of waves is same across all panels. Does that make sense? So everybody has 3 waves for all panels. And that's balanced panel data, but if you don't have that, it will be unbalanced panel data. And then occasionally you have time gaps between panels. So some people actually answer wave 1 and wave 2, but not wave 3, but wave 4. Does that make sense? So some people just answer every wave but wave 3, somewhere in the middle. That makes the analysis a bit awkward and complicated, but here we don't have that in our data. So let's just not think about it here. describe, which will give you the exact same thing from what we saw in the data window. Boolean is the recent 6 months actually, but this is not really used in the data in the model. So the second one is basically you have to XT set the data and then describe the data from the panel perspective. The first command here is XT set. So you have to declare the data as a panel data set. The first should be the ID variable, panel ID variable, meaning that all the time points are nested within the ID or panel, right? So this is the group level. Good. In the HLM terminology. And time or wave is the wave's ID that is indicating what is nested. The time indicator, basically. Does that make sense so far? All good? And then if you type XTDES, it'll be describing the panel data. So, and here is 2248, meaning that there are, even though you have 6,500 something observations, that's not the number of panels, right? The number of panels is 2248. Good. And the T means that there is 3 periods. Okay. And the distribution of T means that TI means that their minimum means that there is there are people who have only one wave in the data, and then a vast majority have 3 waves as their data, all 3 waves. Good. And then you can see the frequency right there. 2,000 something panels have pattern 111, meaning that they have all the waves. And 11 dot means they didn't answer the 3rd wave right here. And 42 people just only answered wave 1 in the minutes. Any questions? And now let's look at XT-sum. XT-sum here shows you the number of total observation, and number of panels. P-bar meaning that the number of waves or the average number of waves across panels, right? So it's close to 3 because a lot of panels have 3 as they have answered to all of the waves. Good. And then the overall mean is basically without thinking any panel structures, you just simply calculate the mean, standard deviation, and mean index. That's it. Just you're not thinking about anything, you're just summarizing the data. Good. And between means that this one is, for example, the minimum here 1, depress level 1 here means that there is a panel that has 1 as the average of depressed here across all time points. It's 111. Does that make sense? If so, you would have 1 as the minimum value. Okay. And for maximum values, they have answered 444 as the depression. If so, they would have 4 as the average panel value. So it's really about average panel values. You aggregate all the data points out by panels, and then you're summarizing the variable. Okay? You're averaging all the variables by panel, and then you summarize it. Good. Any questions? No. And within is about how much changes there is within the panel. Okay. So it's about remaining variance even after you delete all the between variances out. Any questions? Nope. All right, good. And you can see the same thing with female and close friends and family satisfaction. Any questions? Nope. All right. Good. So within this this row really means that really subtracts the between variables, and then you summarize the variables, and that's it. Notice that female variables within the standard deviation is 0 because in this data set, female variable happens to be happens to have no variance across time. There's no shifts in the gender identification in our data. And entity tab will give you this result, meaning that overall is basically just simple tabulation, right? Without thinking any panel structures. But between this one is you aggregate the panel, right? And then you would have that. So there are 1,141 men in the panel data and 1,107 women in the data. And within percentages are 100% because there's no changes across time in the gender identification of the panels. And then let's look at X-trans, which is basically how much transition is there for categorical variables across time. In that case, female variable does not change over time. Female started from 0, and then you end up being 0. Female started from 1, you end up being 1 in the last window, in the last wave as well. Good. Any questions? Nope. All right. And let's look at XT-line command. It'll give you, I selectively chose, I chose like 9 IVs actually on purpose because there won't be a lot of like trends. But XT-line shows you each panel's trend of the variable. So I chose the depression scale in the command, right? Which really shows for this person, ID 14208, this person's depression scale goes really down and stays down, right? And for this person, which is who is ID 14201, this person's depression scale was up there, decreased a bit, and increased a bit later. Good. And this overlay option will give you the overlay of all the trends. Without that option, you will have like separate graphs for each of them. So to combine all the trends into one graph, you need that overlay option. And then if you install XTGraph package, and then run the command, and you would have this graph where all the panels values are summarized here. So the average of the depression scale in wave 1 is about 1.95. And then it went up in the wave 2, and then it went down in the wave 3 on average. Any questions? Nope. All right. So let's take 5 and let's come back to OLS and panel models and interpret all of the results. Good. Right. Let's take 5.
Should we start again? Sure. So let's look at the OLS regression without any consideration of panel structures. So this is regression of depression on OLS regression of depression on the female variable, close friend, and female satisfaction. Alright. This is called pooled OLS, right? Because you're just simply running an OLS regression with the pooled data, panel data, right? As you can see right there, the number of observations is 6,500 something. And as you can see, female variable is significant, close friend is significant, and female satisfaction is not significant but negative. But what would you point out if you're a reviewer of a paper that uses this pooled OLS model? What would you say to that? This could be a final examination, right? I think it's a I think it's a good final exam question. Yes. Yeah. What would you say to this model?
It's just a normal regression, right?
Yeah,
So
just
the
a
errors are
OLS.
correlated, right?
Right.
Because individuals are nested within time,
Mhm.
so the error should be correlated with time.
Yes, and vice versa, right? Time points are nested within panels and vice versa, and therefore the errors will be correlated with each other. What is the problem with that?
Standard error is not
Standard errors
biased.
are underestimated here, which means that you cannot really trust these numbers here. If standard errors are underestimated, then p statistic will be overestimated, right? And therefore, you have false significance. Good. So if you're a reviewer, you should say, oh, you should not use that pooled OLS model. Good. And as you can see right there, if you run the mixed command with the press the same command with mixed command, but with the ID structure or panel structure in mind, and then run the set ICC. The ICC is 44 something %, right? It means that there are a lot of between panel variances that affect the outcome, right? There are a lot of panel mean differences. Some people are depressed in general on average across time. Some people are less depressed on average across time. There are intercept differences. Any questions? Nope. All right. And that's why we want to use panel models. The first one can be between effects models, or effects coming from the difference between individuals. So what you're doing here is to average all the variables by panel. And then you delete out all the within variations. So this command, the command here, x2reg, and all the parts are same as OLSreg, a comma between options. And that'll give you the between effects models results. All right. Does that make sense so far? So this is the between effects models results. Good. And as you can see, the number of observations is 6,000 something, but the number of panels is 2,248. And observations per group, meaning that the minimum is 1, meaning that there are people who answer just one wave. And there are people who answered in all of the waves, 3 waves. And the average is 2.9, which means that a lot of people answered in all of the 3 waves. Good. And if you were to explain the female variable's coefficient, you should interpret the coefficient as this one. Unit increase, one unit increase in female, meaning that compared to men, compared to female, is associated with 0.1339 unit increases in the depression scale on average, but across panels. Right? There is no within changes, within variations in the outcome, right? Does that make sense?
Can you say that one more time?
Yeah. So compared to a male panel, a female panel have 0.1339 units higher depression scale on average. Good. But the point here, the point of the interpretation here is this is about the panel, not within changes across time. Good. Does that make sense? Yeah. All right. And then there is some explanations how these different R squarers are obtained here in the comments right there. There are these formulas, but we're not really required to know that. But I'm just as an FYI, I'm just saying that this R squared is how much of the within changes in these variables across time within the panels are explaining the within changes in the outcome. Does that make sense? That's what within R squared means. And between R squares, or R squared, means that how much of between changes in these variables are explaining the between changes in the outcome. It is just like R squared, but only with betweens. Good. And overall, it's just like Euler's regression, but between between models coefficient. Good. You can see that part right there as well. This is square root of between variance, meaning that you can see the meaning of this part will be clear when you look at the OLS with aggregated data. Next time. So to understand what's going on here, what it means right there, we basically literally aggregated the data. Okay, so preserve means you don't want to harm the data, so you are preserving the data first, and then if you restore the data, whatever change you made within the two between the two commands, they will be restored. Does that make sense? It will go back to the state before the preserve is entered. And then collapse mean, depressed female close friend satisfaction. If E sample by ID means that you're collapsing the data or these variables into the mean values by IDs. So you're averaging all the variables by ID. Right? For example, if you have depression scale of 2, 3, 4, ID is 1, 1, 1, wave is 1, 2, 3. You're collapsing the data into half, ID 1, depression 3. You're averaging them down out. Good. And then if E sample 1 means that just for the sample that was used in the previous estimation. That's what it means. Good. And then you are running the OLS regression, meaning that you are running a between effects model. They're same things. Good. As you can see, the number of observations is 202 something, which is the number of panels. And the F statistic is, you don't really have to know that, but it's just an FYI. The F statistic is 33.08, just like the BE command's results, right? And then the root MSE right there is 0.148, just like this one. Good. So this means that the square root of all estimated errors, the sum of squares of all the estimated errors. Does that make sense? Okay. The sum of all estimated errors squared. That's root MSE, right? So I would like to emphasize that within R squared, between R squared and all of that, this part, all of these parts are not covered in the problem set for the exam. These parts are not covered. All of the interpretation associated with this one, this part are not covered in the exam for the problem sets. Okay. This is just FYI, but I think it's important to be able to write a master's thesis with these models. So that's why I'm telling you that. What's important here is to be able to understand what's going on with the coefficient and how to correctly interpret these coefficients. Okay. For the problem set and exam. Any questions? Nope. All right. And let's look at fixed effects models, which is about x coming from the difference across time within an individual. So this is great. As you can see right there, you can simply, the change is right there. The command is same, right, as the between effects models, but you change the option to FE, fixed effects model. Right. And I'll explain that in a minute as an FYI again. But what's important here is female. Okay. So female variable is omitted because the model is only looking at within variables. How time changes in the variable, independent variable, affects the time changes in the dependent variable. Does that make sense? So there is no time changes in the female variable within each panel, right? It's a time constant variable. So it'll be omitted right there. So if we're interested in the causal, estimating the causal effect of female on the depression scale, you should not use fixed effects models because it'll be omitted. Okay. And and the sigma u means that before the meeting out or before running the fixed effects models, there will be some between variance, right? Unexplained between variances. And sigma u means that square root of unobserved between variance. Okay. And then sigma e means time changes, unexplained time changes within panels. And the row here is the ICC right there. row is this. Good.
You say what sigma u was again?
Yeah, sigma u is before controlling out all the between variance. You are calculating the variance of between variances, between changes in this square.
You move from.
Well, the row is calculated that one. It's basically ICC. Not even base of it, it's ICC. Good. And then so there is a little test that F test that all you this part is not covered in the exam, won't be covered in the exam, but now I'm gonna give you all the FYIs you might need for the master's thesis if you're using this model. Okay. So the last line right there is the F test results with the null hypothesis that all UIs are zeros. So meaning that there is no between variance whatsoever. The null hypothesis is that there's no intercept differences. Then this is the F statistic result, and the p-value is less than 0.0001, meaning that you can significantly reject the null hypothesis that there is no intercept differences. So that gives you the reason why you should use a fixed effect. All right. Does that make sense? Yeah. All right. And similarly, you can also look at this part to see whether you should use a fixed effects model or not. This is correlation between UI and XB. XB means the predicted value of Y, right? There is the correlation between the predicted value of Y and the remaining group averages, and it's looking at the correlation between the two. Right? So it means that if there is a correlation between UIs and predicted Ys, it really means that there is remaining intercept differences even after you explain why with the independent variables you have. I'll give you a graph for that. Again, this is FYI. Based on the X level, right there, you predicted that the Y had to be there, right? But the UI had to say positive. Oh, positive. And then you expect Y to be here, and the waves are right there. There are 3 dots. And therefore, the UI hat, this much is positive, and this much is negative. So does that make sense? Yeah. So you're looking at the correlation between y hat level and this one. And if there is a correlation, and then that means that there's something going on with the shared but unobserved group intercepts. Does that make sense? It might change. That really requires you to change the slope right there. Meaning that there is a confounder, panel level confounders, right? Does that make sense? So it really means that if there is a panel level confounder Z right there, that we don't really observe for U, that are panel level data, and plus, right? But after you, there's plus, right? And as X increases, the predicted value increases, right? But then it could be because U has increased, right? And U contributes to the increase of X and Y. And that's why there are still remaining variances right there. And as X decreases, Y decreases, right? And that's because of U being decreased. There may be a reason. Therefore, U decreases, then Y hat decreases, but still, it still contributes Y directly as well, right? And therefore, the Y hats, the group specific Y hat also decreases furthermore. Am I making any sense? So this part is all U increasing X and X increase. Therefore, that increase Y, right? But there could be some direct relationship from U to Y. And so therefore, if U increases, the predicted value increases, right? Through X, right there. But it'll increase a lot more than that by the direct relationship between U from U to Y. That's the logic behind this statistic. Am I making any sense? Am I confusing you or? All right. Okay. So the last note on that one is basically, what if there is only one wave in the data for a specific person, right? So in the fixed effects model, what is analyzed is within changes, right? Which means that you need two observations. Good. Does that make sense? At least two observations at least. But if you have only one wave, what will happen to that observation? Yeah. the observation won't do anything with the estimate. It won't contribute to anything. Yeah. It won't affect the slope or it won't affect the standard errors. It'll simply be dropped. Okay. So the estimation of this fixed effects models is basically same as it is done by demeaning the data. So what I do here is basically demean all the variables by pins, and then add the grand mean back up to get the intercept. If you see the results, you can see that the mean close friend coefficient is exactly same as that one, the fixed effects models results, right? And FEM satisfaction has also the same coefficient. Does that make sense? Because they are done via same procedures. Does that make sense so far? Good. But the standard errors are different a little bit. Because so let me clarify that on that one. So this one used to xtreg command actually used to use demeaning method. This is more of a older method, but now what it does here, instead of demeaning, you add ID dummies to the regression, OLS regression, because they're supposed to be mathematically equivalent, at least for the slopes coefficients. Does that make sense? So AREG is, oh, I was supposed to have this one. Sorry about that. Yeah, you'll get the same result. So the AREG results will show you the OLS regression results, but you add panel dummies. Right? Does that make sense? Okay. That will give you the same coefficient as the xtreg command results. And the standard errors will also be same, as you can see right there. Right. So xtreg FV will give you the exactly same results as AREG, because they use the same method, that is adding panel dummies. But the demeaning approach will give you the same coefficients, but the standard errors are a bit different because of the degrees of freedom issues, but it's pretty advanced. I'm not gonna cover it, but it can give you slightly different standard errors. Let me tell you that. Good. Alright, good. Any questions? Nope. And then how would you interpret the coefficient right there? Close friend. The coefficient is negative 0.11, right? Meaning that unit increase in the number of close friends is 1 unit increase in the number of close friends within panels over time is associated with negative 0.11 or 0.11 unit decrease in the depression scale over time within the panels. Good. Does that make sense? Yeah. And then you can look at two-way fixed effects models by simply adding time dummies. You can disregard this. You don't have to, interpret these things, but simply treat them as control variables, right? And the next command is simply adding robust standard errors even after you run a two-way fixed effects model, because there could be some serial correlations going on even after you run a two-way fixed effects model, as we saw in the lecture on Thursday. If there's effect heterogeneity, then there could be some serial correlations even after two-way fixed. Good. Any questions? And the third one is random effects model. So random effects models, you can see the first thing you should see here is correlation between UI and X is assumed to be 0. Meaning that you don't really, you assume that there is no confounders or panel level confounders between X and Y. You assume that in the regression, random effects models. Whereas in the fixed effects models, you don't assume that, but you control away all the possibility of that. Does that make sense? Any questions? No? And the coefficients interpretation should be exactly the same as the OLS ones, actually, because it uses both between variance and within variance. And as you can see, there is a partial demeaning approach that you can take, but I'm not going to cover it in the section. But I'll just simply let that have right there to demonstrate how the partial demeaning approach works. But if you're interested, let me know so we can talk about like how it works and stuff like that and what it means, etc., etc. But I'm just gonna skip that in this section. Good. And then let's compare the results. All right. This tab. Right. So after installing the STAB package, let's run the STAB package to see what's going on here. So the first one is OLS results, pooled OLS results. And the second one is between effect, and the third one is fixed effect, and the fourth one is random effects models. So as you can see in the fixed effects models, female variable is omitted, right? And as you can see, the coefficients are pretty consistent and the standard errors are not too different, I would say. Although in the between effects estimator, the standard errors are tend to be really large compared to other models because you're losing a lot of efficiency by aggregating the data. And lastly, I would like to mention the Hausman test, where basically this p-value, the p-value is 0.7, right? The p-value is based on the hypothesis testing, where the null hypothesis is that the coefficient of time-varying variables are not confounded by panel level variables. Does that make sense? So the coefficient of the time-varying variables are not too different when you run fixed effects models. Does that make sense? Yeah. So if the coefficients are really different from each other, different with each other, it might mean that there's a serious panel level confounders going on. Does that make sense? Compared to random effects coefficient, there should be a fixed effects coefficients, right? If you compare those two, if they are too different, and there's got to be some confounders from panel level variables. Good. Yep.
How different is two different?
That's why there is a chi-square statistic, and then the threshold will be 5% for this one as well, for p-value. So it means that you fail to reject the null that they are too different from each other. They are not different from each other. Fail to reject the null that they're not different from each other. So I would use random effects models if that's the case, because it is efficient compared to fixed effects model. All right. Any questions? Nope. All right. Did you find it helpful? Did you find the standard exercise helpful for your, like, say, writing your master's thesis? Or? Sure. Great. So lastly, and this is a bit embarrassing, but I'll show you my master's thesis that uses these fixed effects model, random effects model, and multi-level models. So, the setting here is there is some sort of the data are nested within, time points are nested within each firm, and each firm is nested within business groups. Good. Does that make sense? So there are 3-level structures. Okay. And the Y is some sort of financial measure. You don't have to really know anything about it. But I was interested in interaction between Z and X, where Z is big 4, meaning that there are 4 largest Korean business group in Korea, actually. And then they are frequently mentioned as the big 4 or something like that. And then this is ROE, the profitability, or Tobin's cube, actually, which is some sort of time-varying measure of profitability, or not profitability, but let's say profitability. So this is time constant, and this is time varying. Okay, and obviously this is also time varying. So the first analysis I had is to disregard the first one I had is to disregard business groups characteristics. I had good reasons to believe that. So I considered these 2 levels as important, and then run the panel. And then, all right. Where is it? Okay. Good. All right. Good. The results are summarized as this table, this graph first, but the tables are this one. So the first one is the default, quote unquote, default one. And so these are control variables and intercepts, so you don't really have to worry about it. But there is an independent variable, Tobin's Q, And then what interested me is basically the interaction between tokens Q and the big four variable. The big four variable is time constant. So it should be the main term, the main term will be omitted from this result. But the interaction between big four and tokens Q are time varied, right? Does that make sense? If you multiply these two, they can be time varied, right? So it still holds right there. You can see the results right there. Okay. That was my basis model. But still, like, you would like to see the clean terms effect as well. So that's why I ran. This is divide. I divide the sample to big four business groups and non-big four groups and compare the results. And, which is supposed to be the same thing as the previous thing. But what's important here, I ran a random effects model with the big four here, the plain term included as well. Because in the fixed effects models, it was omitted, right? So to be able to avoid a problem, I also estimate a random effects model as well. And then I also ran a random effects model with a divided sample by before status. And this is a little bit advanced, but so this is the lagged dependent variable by 1 year. So so this is the control. One of the control variables right there is you lag the outcome variable by 1 year. So you use that variable's outcome. So the outcome prior to 1 year is used as a control variable. That way you can control for some sort of latent characteristics of y, basically. It's a one way to control for it, right? And then, oh, by the way, all the variables are lagged, meaning that there is subscripts T1 right there, really small. All the variables have T1 as subscripts, really small, because the y outcome T at T was analyzed with the T1 status. This one is time constant, but for x variables, I use the 1 year prior observation because that would, make sense in temporal sense. And then I divided the sample as well. And lastly, I did 3-level multi-level analysis. Yeah. With the same model. But it's hard to see, but the row ICC of the business group level is really low right there, right? Which means that you don't really need 3-level structures right there. So that's why I use the 2-level structure as the default, right? Does that make sense? But for the business group level, the ICC is really low, 3% or 4%. So I disregard this characteristic and then use the panel models as the default model. But I still as a robustness check or to resolve some concerns that reviewers might have, I added the business groups level and then ran tree level models as well. And then I did not use random slopes model, but I used random intercepts model because I ran random intercepts model and random slopes model, and then there is something called likelihood ratio, log likelihood. And then what log likelihood ratio test does is to compare these two, and then see if they are significantly different or not. So they were not significantly different, so I used this one, not complicating the model too much. All right, good. All of these things are just, not important, but just to show you like what it would look like when you use panel models for your mass releases. Anyways, if you don't have any questions, I'll see you in lecture tomorrow. Oh, what? Oh, sorry. What was the question? So these two are all speaking to the exclusion, not relevance. That's why. Yeah. So if some people say this, this phrase actually speaks to relevance, right? To be able to say that, the outcome should be really tricky, and then be associated should be good as well. But what I was trying to say here is that in combination, they both speak to the exclusion assumption, and then the cause should be changed to be associated.
So for the exclusion assumptions,
Uh-huh.
so we need to assumptions should
Yeah. The verbally speaking, this part is expressed into these 2 points.
and for the start of the series, just says there is like a lot of correlation. So
Right. Yeah.
like there's a lot of like
Oh, between variants,
between various is like
between different panels. Groups of things.
is it like a box time?
No, just intercepts means that constant, like even.
In this year.
Oh no, not. So basically, you aggregate all the variables, right? And then, do we have any variance? That's the question. Does that make sense?
How do you aggregate?
Just average all of the, as I said, so this ID is 1, 1, 1, wave is 1, 2, 3, and Y is 2, 3, 4, right? And then you are aggregating the variable 2, 3. Y And then you ID 1, ID 2, and then you have 7, 3. So you would have 2, right?
Wait, what? So that's the average?
Yeah, this is the you with that data, you're averaging 2, 3, 4.
So it's
This
3 and the 7, 8.
7 or 8 would be
Oh,
6, 7, 8.
Oh,
correct?
right. Oh.
Yeah, and
So
then
that's
is
like
there
the-
any
So
between
that's
there?
like the procedure by ID.
Right.
Okay.
So do we have any variance?
Oh.
Do
Between,
we do actually? But if it's substantive or not, it is a subjective question.
So this is the like intra-class correlations or
Uh,
intra-class.
This
like
is
between variance.
the variance of these will be sigma u.
It's
Yeah,
like between
sigma.
variance.
Yeah.
Between,
And then ICC to be exact is that one divided by total variance.
right, so but when we run the OLX regression, the ICC is large.
Oh,
The ICC is large.
so if you run the mixed command and then you can get the ICC.
Oh,
So
Yeah.
the command actually.
Oh.
So we run the OLS, right? But to demonstrate the pitfalls of that, I use the mixed
it's already mixed command is accurate.
Oh no. Just ICC shows you how that would look like, how the number would look like. Right? When you aggregate all the data and then calculate the number and divide by total variance. You don't. Mixed command per se doesn't do that, but to calculate this one, yes.
You have to like run the mix first.
Right. Yeah. Does that make sense?
Yeah, and you get like, I remember we got like a high ICC.
Yeah, like 44%. Yeah, which is high, right?
So there are between
Intercept differences. Intercept right, across cases, right? It means that you need some model to adjust possible serial correlations because of intercept
So
differences.
serial correlations are correlations between
Serial correlations are errors correlation within across time. Serial correlations means across time, correlations across time,
Right.
but within payments.
So within each band,
Yes.
like within
Right.
various
Because
across time.
oh no, so what I need here is they're mostly positive, right? Because of the between variance, which is the average right there. Because the between variance times are correlated, these points are correlated within that panel.
Between variances, so.
Yeah, between variance, like there's intercept differences, right? This is the gray and the median. And then precisely because you have higher average for the panel for errors, you have serial correlations. Does that, they're mostly positive, so they're positively correlated.
So that's, the serial correlations are.
The errors are correlated within groups, within panels, because it has higher average, higher average compared to other panels. Does that make sense?
So that's like within panel for the cluster.
Yes.
Have you started working on your presentation yet?
No,
No, okay, I haven't either.
I have a paper due on
Thursday. And
For
the leadership
65.
no, a leadership class.
Oh.
That's the final paper, and we're supposed to write like 68 pages.
Oh no.
Okay.
Yeah, I'm not looking forward to the presentation.
I don't
I
know.
like.
Right. I talked to Jim twice last week,
Mhm.
and I made some like modifications on my data set, and I was like making some changes to final analysis,
Mhm.
and I don't know how to like. Do we just put the final analysis on the presentation, or what? Because we're supposed to submit the paper like 9 days after
Right.
presentation.
Yeah, I just think. Like, I don't know. I would just put what you have. Like, and it doesn't have to be like super specific, but just like general, like what you found.
I thought we could just like roughly speaking about how we start doing
Right.
analysis and
Yeah,
what
I
like
think that's
problems that we
fair.
encountered in the process.
Yeah, that's the one thing. It's he's nice through the presentation when we can like we still have weeks to submit the paper, so it's kind of like you don't have your final analysis done.
And it's like 16 to 17 minutes.
I know.
I was like, I will speak really slowly.
Yeah,
on
exactly.
Wednesday.
Yeah.
Are these free snacks?
Yep.
Oh, are these from you?
Yep.
Oh, thank you, John.
Uh huh.